Casey and I have been going through some questions on the forum, and you know a lot of their questions just because you're on the forum so much, right? But one of the major questions that I think people are wondering is, since you're a digital engineer, what makes you so qualified to make a headphone amp?
Okay, first of all, actually, I started the whole design career whatsoever from analog. And actually, analog is a very important part of digital. I don't know if you guys know that every time clock in digital circuit is analog. And actually, a lot of our product, like from DaVinci, Geek Out, Geek Post Stack, half of them are analog too.
Yeah, that's actually one of the things that we got. I mean, a lot of the positive reviews of DaVinci in the early on stages was the analog implementation, right?
Yeah.
But what about a headphone amp?
Yeah, actually, for example, this guy, the Geek Out, the bare boards, you will see a lot of USB implementation, DAC implementation here, but from the section all above and including this part, you will see a perfect headphone amplifier here, small sized, about this half. From here all the way here, the headphone amplifier, and you can even drive the line out, right, and have the headphone amplifier. That's a small version. And actually, for the one you saw here, this guy, GPX, don't worry about this part. There's a line out. The whole thing here is a headphone amplifier. It's a differential, balance, and has single-ended output here too. So actually, I'm doing the headphone amplifier for quite a long time, and thanks, a lot of people love it.
Yeah, cool. What? Let's see. There's a couple questions here. The first one I thought was kind of fascinating. They're wondering why on earth we would want to put 10 watts out into a headphone.
Okay, first of all, a lot of speakers users, they use 1000 watt power amp there, right? And people ask them why. Their answer and my answer is the same. You need to have the headroom, and when you need it, you can use it. When you buy a Ferrari, you won't drive 160 miles per hour every day, but when you need it, you can use it. First. Second, I think the most important thing is when you have a higher power output, you can, assuming the whole architecture, the circuitry, the capacitance, whatever, the power reserve is there. So it definitely will help you when you even need 1 watt or 2 watts. And considering that, I don't know if you guys check this. Here, let me.
Oh, right.
Yes. Some people ask what's the 10 watts rating, what's the low? It's 16 ohm. But a lot of you won't use that 10 watt to drive 16 ohm, but you will have 300 ohm. Like for example, like Sennheiser HD 800, it's 300 ohm. So you will see that when it goes to 300 ohm, actually it becomes 560 milliwatts.
About half a watt.
Yes, half a watt. So in order to get the higher output when you have a higher resistive or impedance low on your headphone, you better have a better watts. You will hear more headroom, more punch. Everything will get better.
Okay. Let's see the next question. Oh, speaking of, okay, so we have all this headroom. Say we have a 10 watt headphone amplifier and we're using something that has a 32 ohm load or something. Obviously the users are going to be attenuating down quite a lot. So they're wondering what's the implementation of the volume attenuation?
Oh, that's a good question. First of all, before I answer that, I need to answer the other questions. I think they should have. We have 3 outputs here, right? One is balanced output that can goes to 10 watts. The other is a 1/4 inch normal headphone output. The other little guy is the TRS for the IEMs. Each of the output connector have different wattage ratings there. So 10 watt, we are talking about the big guy, the 4-pin balanced output. The little guy, we got roughly 100 milliwatts there only. So each output, I already set the different voltage gain, different current gains there to specify the special need for each type of headphones. So when you do the volume attenuation, you won't need to do too much. For example, you won't connect your IEM to that 10 watt output. It's too much. We designed a very versatile solutions. You just need to connect to that IEM. You need to attenuate some, but not much. I think that's the best approach on the market. So again, the big tank, I give you 10 watts. The little sensitive IEM, I give you 100 milliwatts, and every connector can work at the same time. So you can plug 3 headphones into one headphone amplifier if you want to.
Does that sum the load though?
No, it's separated.
Okay.
Oh, I forgot to say, it's separated. It's separated. Every connector has its own circuit. It's separated.
Okay. So let's go back to the implementation of the analog volume control. What are your plans
Okay, the best way to implement the analog volume control, first of all, the whole machine, the whole device needs to have an extremely low noise floor. If the noise floor is too high, you basically won't get any benefit from analog. So first of all, we need to have a very extremely low noise floor. Second, I would love to do a 4-way, not only 2-way, 4-way is a fully balanced analog volume. So for example, it will be left channel plus, left channel minus, right channel plus, right channel minus. Four phases, 2 channels operate at the same time. So it will attenuate down either for both balanced output and single-ended output. I think that's the best way to do it.
How do you go about getting the lowest noise floor?
Including 3 things. First of all is again, go back to the fundamental power supply. Since this unit will work with LPS already lowered the noise to roughly 10 to 12 microvolt. It's really, really low. And I will use the shunt regulator, local regulator, multi-stage regulator to make the output stage even lower noise. That's the first thing. Second is I really believe that when you do the PCB layout, let me show you. Yeah, use this board as example. Okay, make it red. Okay.
What board are we looking at?
It's the... Oh wow, should be the VIDAC board. VIDAC board.
Okay.
And checking this out. See, every layout, every resistor, feedback resistor, gain resistor, whatsoever is so close to the IC. So we don't have any physical distance between the passive components and active components. So everything we will try to limit the potential, any interference to the minimum. So that's the second thing. It's a regarded layout, very important, but not every engineer pay attention on that part too. The third thing I want to say is you need to pick the best passive components, not only active. Active is important, passive is important too, including what's the resistor you use, what's the capacitor you use, what's the PCB stack up you use. Everything will affect the noise floor. So you put every effort, including layouts, architectures, best components all together, you will get the best result. Sorry, the answer is a little bit long, but
I guess the last question is people want to know about the fully balanced DC servo protection.
yes.
What is it? What does it do? What's the benefit, and how do you do it?
All right. In the first generation, 2 years ago, we have geek out. Due to the size limitation, we don't have DC servo there. The reason why I need to have a DC servo because I insist, we don't have any capacitor in the signal path. It's digital in DC out. So we don't have any capacitor in the middle of your signal chain. So that thing won't decrease your sound quality at all. But in that case, we need to have a DC servo sometime to lower the DC output. So on Geek Out, we don't have the space to implement that, but we implement that in Geek Pulse. In HPA, we will make it even better. We will have the best precision op amps to monitor if there's any little DC. I want to make it lower than 0.5 millivolt. Make it even lower. It will constantly monitor any potential DC component on the output. The reason why we said balanced, because on the XLR 4-pin, we have, again, left plus, left minus, right plus, right minus. We will have 4 DC servo constantly monitor this 4. So we have separate 4 DC servo watch over this 4 outputs. So everything will down to almost 0.